to have the lecture of N.Olson. N.Olson is at the end of his PhD at UT Austin in the Department of Electrical and Computer Engineering. He's interested in the various type of questions related to 6G communications, particularly with joint communication and sensing. And he developed very interesting tools under the supervision of Jeff Andrews and Robert Heath, using stochastic geometry to understand and define the capacity of not only communication, but also sensing. So, Nick.
All right, yeah, thank you. So today I'm going to be talking about some of our recent work. The title of the paper is Coverage and Capacity of Joint Communication and Sensing in Cellular Networks. It's currently, under review for transinfo theory, but it's on our archive if you would like to check it out further after the talk. Let's see. All right, great. So yeah, just like a brief overview. I'm first going to talk a little bit about joint communication and sensing, about what we're trying to do with this project here. One of the challenges is in analyzing, joint communication and sensing at network level is how one would define metrics for performance for both functions, primarily for sensing. So we'll talk about that a little bit. And then, following the development of these metrics, I'm going to develop a model for what we see as sort of a typical JCAS network, with the goal then being to analyze this network using tools from stochastic geometry to draw conclusions about the performance of both communication and sensing. Following this, I'll briefly highlight some of the analytical results and the way in which we got the results, and then present some insights that we can get from these through a numerical case study. So yeah, just like introduce joint communication and sensing. It's an interesting concept that's being floated for potentially 6G networks. And the main idea basically is that you're going to use network resources, so that includes hardware spectrum, potentially even waveforms as well, to simultaneously, in the same band usually, perform communication to users and possibly detect and track targets within the network. It's mostly envisioned as a function that the base stations would perform, although of course, user equipment could perform their own sensing. For instance, if you have some sort of automated vehicle, that could benefit from that as well. But we're going to mostly focus on the case where it's network side sensing. This isn't just sort of like a random idea for throwing two technologies together. It could potentially facilitate some interesting use cases. So, a big one would be driverless cars. You could use the network to provide increased spatial awareness, perhaps to monitor roadways or to, direct vehicles a little bit more intelligently. Also could play a role in augmented reality, extended reality, or the metaverse applications. Another interesting thing too is that sensing isn't something that is limited to its own focus. It can also aid in some challenging communication tasks, for instance, beam alignment and tracking. And you can think even of sensing already being playing a part in certain communication processes. For instance, channel estimation can be thought of sort of as a coarse form of sensing. So the two could benefit each other certainly. And finally, it's not just that this is an interesting idea. Trends in wireless networks are also making joint communication and sensing more feasible. As RF front ends, the radio architecture is becoming a little bit more generic. More processing is done at baseband. It's now capable of performing both functions. Of course, as we're moving to higher carrier frequencies, that's something that's beneficial for communication in terms of improved bandwidth, and improved bandwidth is also helpful for radars, improves range resolution. As we're moving to millimeter wave, we're starting to use higher dimensional antenna arrays with improved beam width. This helps for radar too, because then you have improved angular resolution. There's a variety of ways in which one could perform sensing using base stations. The simplest setting perhaps would be with monostatic sensing, where the base station is both the transmitter of the waveform and the radar receiver. In that setting, basically you can only get real certainty about where targets are if they're line of sight. If you have an line of sight path, it'd be impossible to tell if that's from the same target or from a different target that's at a range that's farther away. So density in cellular networks helps improve this line of sight coverage in that regime, which is what we consider. And finally, as the networks have switched, from 4G to, well, I guess it was used in 4G as well, but OFDM has become the dominant waveform for communications. And although there are other waveforms for radar that potentially perform better, OFDM does perform quite well with sensing. So at least in the waveform domain, it's feasible to do both. And finally, I mentioned monostatic sensing. This sort of implicitly requires a full duplex transceiver. There's been a bit of work on this, including some students from Professor Andrews' group looking into the feasibility of this. Still developing technology, but as progress is made in this area, it's something that could potentially help with joint communication and sensing. So what we're interested in is addressing the performance of joint communication and sensing from sort of a network viewpoint. There's certainly a variety of questions that one could ask in this regime, but we're interested mainly in characterizing the joint impact of intercell interference on the performance of both functions. That's something that has been understood for communication networks, of course, but moving sensing into a bigger network setting is something that's perhaps less common, at least in classical radar analysis. So developing practical models to capture this phenomena is important for both addressing this and understanding how networks should be designed. It's also important to develop a model that's able to jointly comment on the impact of intercell interference on both, not just to do one or the other. And so what we hope to do, or I guess what we did in this, is basically to extend some of the tools from SNR stochastic geometry. It's been a powerful framework, of course, for characterizing the impact of intercell interference on communication networks. And so what we intend to do with this is to extend these tools to capture the performance of radar tracking in a JCAS network. And what we mean by radar tracking is basically the parameter estimation side of radar. Typically, there's classically two functions. One is detection, in which you're trying to determine the number and at least approximate locations of targets. Typically, the waveform will tessellate space into certain resolution cells, and the detection problem would be determining whether or not you think that there's something within a cell or not. Radar tracking then would be taking these detection measurements and further refining estimates of the parameters of interest. So this is something that hasn't been considered quite as much before. There's been some prior work that have considered, somewhat simple models of detection and joint communication and sensing, but the tracking side hasn't quite been addressed. One of the challenges here is accounting for the complexities in the return. Yeah, I guess in addition, there's a need to consider what it means for the radar function to perform well. Hopefully, to do this in a way that is easy to discuss in terms of sensing. So basically, given this, the objective of our project is sort of twofold. The first is to investigate sort of what a meaningful notion for sensing performance, specifically sensing coverage, would be. We end up using a formulation based off mutual information between the radar return and the parameters of interest. So this admits interpretation in terms of capacity, which is nice, when talking about joint communication and sensing. And basically, given this metrics, we seek to characterize the impact of intercell interference in sort of a typical JCAS network using tools from stochastic geometry. So I guess I touched on some of these points a little bit, but what we do specifically for this metric is that we begin with the mutual information between the return and the parameters of interest. This is unfortunately generally intractable, so we employ an approximate lower bound on the mutual information. and use this to sort of define the performance of a return, and then extend the notions of coverage and capacity based off of this mutual information object. If you treat it like the capacity of a channel, the notions of coverage, probability, and ergodic capacity sort of generalize nicely, which is nice. As we'll see, this expression is has some desirable properties in that it's also related to common distortion metrics, specifically error covariance. And this expression can be quantified in terms of something that looks like an SNR function and allows us to use tools from SNR stochastic geometry. Basically, from this notion of sensing performance, we then go on to define what it means to perform well in the JCAS network. And qualitatively, this is basically going to be the fraction of UEs and radar targets which are covered by the network in the sense of the channel capacity and this notion of radar capacity that we employ. One of the nice aspects of this formulation is that when the radar processes and the target processes are independent, the ergodic theorem actually allows us to separate the analysis of both sensing and communications. Even though in the actual network of that we're modeling, it's something that's happening jointly, even with the same waveform. And then finally, given this, these metrics, we characterize the sensing capacity of this representative network, which we model. We specifically consider a network in which we're using a multi-carrier sort of OFDM waveform, directional beamforming, monostatic base station side sensing. This a little bit of a challenge involved in getting some tractability for this SNR type function for the radar. So we developed some approximate upper lower bounds for these models. Within the paper, I'm not going to be able to go through all of them, but we developed some interesting results that might be of independent interest, including a method to obtain sort of closed form upper and lower bounds for interference Laplace transforms, and some generalization of Holder's inequality. It's a little bit technical, so I won't spend too much time on them. So just to provide a picture, I guess, of the network we're considering, a joint communication sensing network might operate in something depicted in this picture. These orange sort of hexagons are base stations. These triangles are users. The squares could be objects that the network is trying to sense. And these nodes basically are using a common waveform to both perform downlink communication in the regime that we're considering, and then use these reflections to track objects in the network. So yeah, it's just sort of a picture to keep in your head as we're going through some of the results. So I guess on to the first major section, sort of discussing the notion of capacity that we're using, how we define it, what it looks like specifically. And then we'll go on to some of the network model analysis. So I guess, so qualitatively, basically what we're seeking to do is define a notion of, what it means for sensing coverage and communication coverage to happen. And one way you might do this would be to say that, it's the coverage probability, for instance, could be the fraction of UEs, which obtain sort of a sufficient quality of service. This quality of service you could define in terms of the Shannon capacity, and you basically get a classical metric of coverage probability, which you can use quite widely in stochastic geometry analysis. But then for UEs, since we're considering the radar tracking case, you could do a similar notion. You could say that, the radar targets, which we term as SOs. Since we're considering the radar tracking case, what we're really trying to do is to refine the estimates of the parameters of interest associated with these objects. In this regime, you can sort of think of it as a non-cooperative communication channel, and then the goal would then to be able to provide sufficient quality of channel to refine our estimates of these parameters of interest. So basically, I'll start with the sensing case. So to quantify the sensing performance, we could begin something like this. over some time interval, the base station that would be responsible for the area in which this sensing target or sensing object lies is going to be, scanning its beam over space as it's transmitting the waveform, potentially also using this waveform for downlink communication. It's going to be listening for the return. This return we're going to let be, just generally denoted by this variable y here. And it's going to use this return basically to refine some parameters of interest. Typically, this could be Doppler and delay or angular position. For now, for the purpose of discussion, we'll just let this be denoted by theta. So given that we have this return, we might say that the tracking of an object is successful if the mutual information between this theta and y, the radar return, is above some threshold when theta is distributed according to some reference prior. This reference prior might seem a little bit odd, but it's basically meant to capture the notion that we want to provide a fair metric for coverage. So if you're in a case where the base station knows the position really well, the mutual information is going to be really low, but that's because we already have a good prior belief. So by looking at the mutual information between the return and theta with some reference prior before it provides sort of a way of quantifying the channel independently of our what the specific beliefs about the parameters of interest at each base station might be. This you can think of this potentially as in terms of channel capacity for a UE. The channel might be able to provide a quite high data rate, but at some instant in time, the UE might not really have a lot of data that needs to be transmitted. So it's something analogous to that. So given this formulation, ideally what we'd like to do would be to define something that we're going to call radar capacity, which is basically the mutual information divided by this TCPI, which is in radar terminology, the coherent processing interval. It's basically just the time in which it takes to collect the measurements that we're using to refine our estimates. So this is an interpretation of the information we get from one sensing procedure. Unfortunately for our case, this mutual information is generally intractable. Excuse me, and that's because the radar waveform is perhaps somewhat complicated. Things are very much non-Gaussian, so you get some nice expressions for the mutual information popping out. But thankfully, we can provide sort of an approximate lower bound for the mutual information, subject to some technical considerations on the underlying probability measure. Mostly just that the parameters of interest need to either lie on the be a real number with the support over the reals, or a positive real number, as long as it's not restricted to a sort of a closed set. But anyway, in this case, you can get approximate lower bound in this following function. So it's we have these terms here. This h of q inverse theta basically is the differential entropy of the prior, but scaled to the unit covariance. So if we assume that the covariance of the prior is q, that's where the q comes from. But this term outside the log basically doesn't depend on the covariance. So the interesting term here is on the right is this log determinants. It's a density plus a scaled version of the Fisher information matrix, which is a metric commonly used for radar. And this log determinant function is nice because it has the interpretation of the sort of typical reduction in error covariance over the sensing interval. This bound is approximate, and that won't go through the whole details of how it's derived, but basically you have the MMAC covariance popping up in the lower bound. So to get some tractability in that, you can further lower bound this by the Fisher or Bayesian Fisher information. So if the MMAC for our problem is close to the Bayesian Fisher information, we're going to get this is a non-approximate bound. But since we're if we're defining coverage in terms of this mutual information being above some threshold, given that constant term outside of the log is sort of something that doesn't quite depend on the properties of the channel or our prior covariance, I think it makes sense to consider approximate notion of radar capacity given by this more friendly log determinant formulation here. And as again I mentioned, this basically represents the average reduction in error covariance from providing a sensing interval. The term that really depends on the channel here is this Fisher information. So that's what's going to be important for characterizing the channel quality. And like I said, for for using this for coverage purposes, it just differs by this lower bound on the mutual information by a constant factor. And similar to use this for capacity purposes, the ergodic capacity would also just be off by a scale factor. So I think it at least makes sense to use this.
So
and I'll note,
can I ask a question?
Yeah.
In the earlier formula, you had some extra term with something that looked Gaussian with this log of 2p, and
yes.
Why has this disappeared? I'm not sure to have grasped the connection between the earlier slide and that formula.
So this C tilde rad formula and this one?
Yeah, right.
Oh yeah. Yeah, so basically for this one, this H of Q inverse theta, this scaled version of theta basically has identity covariance. And then this other, so basically what I'm arguing for is treating this sort of like a constant that we can ignore. And the reason for this basically is that it doesn't depend on the properties of the channel. It's just a function of the prior. It also doesn't depend on the covariance of the prior since we've scaled out the covariance. And given the fact that we're treating this prior as sort of a reference prior for each of the base stations, this would just be something that would be a constant factor from the perspective of this mutual information. And
thank you.
Yeah. All right, and I'll note that this metric that I discussed here has been used in prior work under the term estimation rate, but it was derived under assuming that everything your prior was Gaussian and your measurement model could be reduced to something that was an additive noise model with Gaussian noise. So this is just perhaps a little bit more a generalized way of using the same result, but it has been used before, so it's not 100% unique to me. But unfortunately, we're not quite done yet because we need to get something that is actually tractable for the purposes of analysis and at least in the stochastic geometry framework. The Fisher information has a nice form, but the determinants makes that expression nonlinear. So what we do to further add tractability is develop these upper and lower bounds on this C tilde rad equation that we introduced. And what you can get is that it emits upper and lower bounds in the forms in terms of this object called SNR Rad. This G function is a constant basically that pops out from the Fisher information that just depends on the waveform parameters as well as the prior covariance. And I should mention that we get this since we're considering a OFDM waveform. This is derived in the setting where we're using an OFDM waveform, and that's how we get the expression for the Fisher information. So that's basically where it pops up. And then the upper and lower bounds come from using some tricks to get some upper and lower bounds of the determinant in terms of some function of the trace. When you take the trace of that, you basically get this SNR Rad function popping out here. And what this is that, if you're using an OFDM waveform for sensing, you're potentially allocating different resource elements for that purpose. So you'll have a specific SNR per resource element. And then the Fisher information will weight those in a specific way that sort of quantify their importance for the purposes of parameter estimation. What we've done is basically just normalize these factors here so that they sum to one. You can think of it then like this sum is sort of the average SNR we see over all the resource blocks, resource elements that we're using. And this term is actually similar to something that's been called integrated SNR in radar. yeah, and then these constants again depend on the Fisher information. So what we get now is something that looks a lot more similar to the Shannon formula, but it's really mutual information for sensing, and our goal is to use this to find coverage. And finally, to characterize the communication performance, the quality of service, we'll use the Shannon capacity. So since we're considering sort of more of an OFDM waveform, following prior work, I think it's reasonable to consider just the performance of one resource element. The reason being that, if your SNR distribution is stationary, for instance, the ergodic capacity would just be off by a scale constant. And in some prior work, coverage expressions have been determined that are functions basically of a single resource element. So that's basically the metric that we're going to use for sensing. So to relate this an expression that's similar to the sensing capacity, what we have here is that if we let T estimate the OFDM simple period, if we treat interference as noise, the capacity of the channel would be given by this more familiar 1 plus log SNR formula. So basically, So in putting these together, we can then characterize what we call the joint communication sensing coverage and capacity. Basically, the coverage probability then would just be a fraction of UEs whose SNRs from the perspective of the serving base station is above some threshold. Given in light of the way that we've characterized the mutual information for sensing, we could characterize the sensing coverage in the same way. And similarly, for ergodic capacity, it could be the expected value over these rate functions. But formally, though, if we think of this in terms of spatial averages, if we let phi s and phi u denote the radar target processes and UE processes, and we can think of coverage probability as sort of the spatial average of all users whose links are above some threshold. A nice property is if these are, ergodic and independent processes, you end up with something that's sort of a weighted sum of these coverage probability for sensing and a coverage probability for communications, which is pretty nice and similar for sensing. So in our following analysis, basically what we can do is analyze communication and sensing jointly in terms of these performance metrics, even though in the actual network, these two things would be, we can analyze these separately, even though in the actual network, they would be happening jointly. All right, so basically, given this discussion of metrics, we can then use them to characterize performance in the network. Basically, the key aspects of the model that we're considering, we're going to sort of basically consider what we think to be a representative network. So the network is operating in the millimeter wave band, which operates, it has sufficient bandwidth for sensing and sufficient directionality to provide good angular resolution. We're also considering a common OFDM waveform, as I've alluded to. We're considering the case where we're serving downlink users and tracking radar targets in a monostatic setup. We can think of, since this is in a cellular network, sensing and communication are going to be cellular. And what we mean by that is that, UEs, of course, are going to be associated with the base station with the strongest signal, or lowest path loss. For sensing, though, you can think of it as each base station is responsible for the closest region in space, basically the Voronoi cell, for the targets in that. This is basically a crude form of network sensing. And basically, as samples are collected by scanning beams over space, we both communicate to downlink users and form belief about targets. See. Oh, yes. Sorry for that. So basically, within this framework, we can characterize these performance metrics, which I've just discussed, and allows us to basically determine in a common framework the impact of intercell interference and the performance of both functions. Basically, the modeling aspects we're going to go through is basically trying to formally describe what's going on in this picture here. So we're going to go through each of these components, some of the spatial model, the impact of blockages, directivity, path loss. All these factor into these SNR models, which then determine performance. For the spatial attributes, we're considering sort of Common assumptions, the base station process is going to be assumed to be a Poisson process on the two-dimensional reals. For the probability of blockage objects, we're going to say that a link between some point X and another point Y, where X comes from the base station process, follows the independent exponential blockage model, where the loss probability is given by this basically distance between the points scaled by some factor beta. And we can sort of succinctly represent all of these in a single process, where if we let MK sort of denote the mark of whether or not the base station is line of sight to the origin, XK and MK would then be the joint process of these points and marks. And then for, some further definitions of some of the functions, it might be useful to talk about just the line of sight points or just the non-line of sight points from the base station process separately. So we'll denote that by phi L or phi N when it comes up. As far as the path loss goes, basically what we're considering, again, is that sensing is going to be line of sight only since it's monostatic, but communication could potentially be line of sight or non-line of sight. So for the communication case, that means that the path loss is going to be random. It's going to follow a line of sight law if it's the base station and the UE are line of sight, or a non-line of sight law if it's non-line of sight. And we use basically something that looks similar to sort of a generic path loss model with this K times R to the negative alpha term, but we also add this exponential factor here. This is something that's pertinent, at least to higher millimeter wave, and can count for some absorption phenomenon. But if you would prefer that the model didn't have these parameters, you could also set those gamma factors to 0 and obtain results accordingly. So that would be the path loss for sensing. For radar, though, we use a slightly different path loss function, but which accounts for the fact that the signal is both propagating out to the target and being reflected back. You can show from the what's called the sort of two-way equation that you'll basically end up scaling this line of sight path loss. The exponents get a factor of 2, and you would further attenuate the dispersion by another factor of 4 pi in the path loss intercept. So further, we're going to assume that the base station, UEs, and the receiver, the serving base station are employing directional beamforming for the purposes of communication and sensing. So to model this phenomena, we employ a sectored model. Within the main lobe, you get sort of a max gain. Outside the main lobe, you get a reduction, where the main lobe would have a beam width, fixed beam width of delta 3 dB here. Sort of to
question on the quick question on the beamforming.
Yep.
So there is an initial access problem, right? You want to detect this, right? And so, how do you handle the beamforming, the sequence of the search in order to discover the objects?
Yes. So the search basically would be performed by beam scanning. So over some time period, you would scan your beams over space. As you're scanning your beams, you can also use the data or the waveform that you're transmitting to communicate with downlink users. And then that would be sort of this big mega sample that would account for all the targets in your vicinity. So for the purposes of, well, I guess we're considering tracking, but for the purposes of detection, then you could provide, use a variety of methods. A lot of them are sort of correlation based. Basically, we're correlating over the angular domain, the delay domain, and the Doppler domain to determine the approximate presence of targets, and then using some thresholding. But then following that process, you could basically focus down on one of those beams, basically, wherein a target lies to further refine the estimates.
Thank you.
But yeah, yeah. I guess this is taking a little bit longer to get through than I had envisioned. So I'll I guess I'll briefly go through some of the other aspects of the SNR model. So basically, I think this is an important factor here that we can still use something that looks sort of like Rayleigh fading for both communication and for sensing. So if we assume fading in the desired signal is exponential distributed, we know that this gives us some tractability for classical stochastic geometry analyses. This is a simplifying assumption for sensing. You know, in millimeter wave, especially, the fading wouldn't necessarily look exponential. But you know, prior work has looked into how much you're losing basically in terms of tractability or in terms of expressiveness, and the gains basically in terms of the tractability that you get are quite outweigh the drawbacks in terms of the expressiveness. You know, if you don't, or sorry, in terms of the tractability. So we're going to consider Rayleigh fading for the communication signal. Since we're considering line of sight sensing, there wouldn't necessarily be a strong fading impact for sensing, but there would actually still be some fluctuation in the received signal that one could treat similar to fading, and this is due to the radar cross-section of the target. So if you're considering, you know, targets are generally points, but if you consider a slightly extended target where there's potentially reflectors that are closely spaced, you'll get some phenomena in the return that is similar to Rayleigh fading. This is called a swirling free model, and it's what we employ here too, and helps to get some tractability. Yes, I'll just also briefly point out that the radar return is happening over now, since we're using sort of multiple resource elements and time slots to perform sensing. We now need to consider sort of both wideband and some temporal aspects, which I think is worth pointing out. So we're going to let this matrix, which we're calling SRAD, denote the resource elements that we're using. So you can think of this as arising from the beam scanning procedure. Every time your beam hits your target, you know, that would basically chop up time. It can also potentially be advantageous to not necessarily activate all subcarriers, which can help with range resolution. This can be sort of like a sparser matrix indicating which resource elements you're using, both across subcarriers and across time slots. And in general, our return depends on all of those. And this basically means that we need to consider potentially some temporal dynamics due to time varying interference effects, as well as sort of frequency selectivity. So I think, you know, for the purposes of time, I'm going to jump to the SNR models. I apologize for not going through all the notation. Actually, before I get to the SNR models, let me briefly point out an important feature of the model for how one determines the association of the which target gets tracked by which base station and which UE gets associated with which cell. So we're going to say that the location of the serving base station, X0, for the UE basically is going to be determined by the one with the strongest path loss. But you know, this is sort of a typical assumption, and it makes sense. You know, the base station with the strongest path loss will on average give you the best performance.
Nicolas?
For sensing, yeah.
There is a question. Stefano, you can ask your question by audio.
Can you hear me?
Yeah.
Yes.
Okay. I was wondering if you consider the self-interference, the effect of the self-interference on the sensing performance.
Mm-hmm. Yes. So that's not a factor that we explicitly add. I know it has been added in some prior work. It would end up basically adding a term in the SNR expression. But yeah, that would be a phenomenon that you, in general, would need to account for with full duplex. Although, if one is able to slightly adjust the transmit and receive beams, it can be reduced by a fair bit. There's actually been some interesting work by students of my advisor's group, where he looked into basically, if you're adding small variations to the transmit and receive beams, you can get, several, I think over 10 dB drop in the self-interference between the two beams. But it would be, yes, an important phenomenon to consider. All right.
Yeah, thanks.
Yeah. And I'll briefly, just say for the sensing object association policy, you can similarly say that the closest base station would be the one responsible for tracking it. This would be sort of a form of network sensing, because in general, each base station is going to be able to see many of the targets, perhaps beyond this cell. But if there's some sort of central coordinating unit, one would be able to determine, hey, this base station thinks that the target is in one area, this base station thinks that this target is another area, and this region seems to be relatively close. So we're going to use the estimate from the base station that's closer to this point. That's sort of implicitly what we're saying by this rule here. I guess, I haven't gone through all the notation, but basically we end up with these SNR models which look like this. So I'll just review the terms. So for the SNR com, this H naught is basically the fading term. For Rayleigh fading, this L is the path loss from the serving base station, which is determined by this association policy. We then basically have interference plus some sort of normalized noise variance. The interferers have fading. This BK and ZU basically account for the transmit and receive antenna gains, which may or may not be aligned. For SNR Rad, we basically have a similar form, except we're now averaging over the resource elements that we're using for sensing. So these theta T's are basically just derived from these A to M factors that I defined earlier, but we've sort of we've summed up some of them so that they're basically now in the resolution of time slots, which is where you might see other base stations in the network changing their beam pointing directions. Since sensing is line of sight only, we have this indicator function out here. So if a point has no line of sight base station, then it basically won't receive any service from the network. One subtlety I'll note too is that because the base station is both the transmitter and the receiver, the path loss from the interfering base stations now isn't the origin. It's going to be wherever the serving base station is, or the distance between the serving base station and some interference, say at xk. So these are basically the models which we now seek to analyze using more conventional approaches from stochastic geometry. All right. I think I'm gonna have to. Sorry, I apologize for this is going. We need to speed up on some of these, but I'll just briefly summarize what we're able to do. So basically, our general approach, since we have Rayleigh fading the signals to sort of exploit this exponential variable and then characterize these SNRs in terms of their Laplace transforms. The challenge, though, is that for this SNR Rad function here, the fact that we're performing averaging over the resource elements complicates analysis. So to get around this, basically, we identify this summation with these weights here as sort of the harmonic mean, basically, of the interference. And the long story short is that one can get upper and lower bounds by changing this type of mean. So if you turn it into the normal arithmetic mean of interference, one gets a lower bound. If you turn it into a harmonic mean, you get an upper bound. We also show that you can get an approximation in terms of the geometric mean. And what this boils down to further is that you basically, this sort of averaging, you can pull it inside the summation over interferes using sort of something that generalizes Holder's inequality. And then what one has is that you need to basically just characterize the Laplace transform of the interference in conventional ways, but the analog of the fading term, this HNBT-ZB, is now going to be the part where the averaging takes place. So getting the Laplace transform of that is potentially a little tricky, but if one can do that, then you can use sort of conventional methods. So that's the main approach. We also get some ways of getting some tractability in these Laplace transforms. But that's sort of the main idea. I think for the sake of time, I'd be happy to talk about it more afterwards. I might jump to the numerical results, just to sort of show some of the insights that we can get using this analysis. Basically, we consider a scenario which we've parameterized the network where the base stations are basically trying to track objects that would maybe be traveling at vehicular speeds and ranges. So there's a lot going on in these figures, but basically what we're doing here is showing the communication coverage performance and the sensing coverage performance in this common framework. So there's a bunch of curves here in the sensing bounds. So this green one up here is the SNR, so it's what you get if you didn't have any interference. Then we have a series of bounds and approximations. This yellow one is the lower bound, basically. We have this purple one over here being an upper bound. We've called these, SNR, HM, AM, or GM. The ones to look at here are sort of these thicker ones in the middle here. These blue ones, which are our approximation, which actually is pretty close to the simulation results. But the key takeaway here is that, the SNR of radar is going to be quite low. This is because of the two-way path loss, certainly. So in this case, sort of the median SNR is close to 0 dB for radar. Of course, this is about the integration gain. But for communications, given the way that we've parameterized the network, this being a millimeter wave with fairly narrow beam widths, we actually get quite high SNR of close to 50 dB. But interestingly here too, one of the takeaways is that the impact of interference is actually stronger on sensing in terms of communication if one defines this impact with respect to the SNR. There's about a 25 dB gap for sensing instead of a 15 dB gap. And this would even further be made worse if we added in some of the self-interference effects. So sensing, interference is actually going to be perhaps a stronger phenomena for sensing than for communication. It's going to be something that these networks are going to need to address. Interestingly, you can also, in part of our analysis, decide to look at how the capacities.
Hello, short question.
Yes.
Could you explain
Yes.
the rationale for the gap being higher in sensing between SNR and SINR? What is the rationale? What is the explanation?
Yeah. I think one of the things that we have going on here is that sensing is occurring over a wider time scale. So within this time scale, there's a greater chance of you getting some more main lobe interferes than for communications, for instance. And since we're averaging over this, you're basically pulling in perhaps interference that might be a little bit stronger than in the communication case. It's still something I'm trying to figure out, like what's the best explanation for this, but this I think is at least one potential explanation.
Okay, thanks.
And then finally, we can look at sort of the capacity scaling trends. This would be the expected values of those rate functions, which I defined. So on the left here, we basically have how sensing scales with the average cell radius, or sort of the proportional to the inverse of the density, and similar for communication. The important curves here are basically sort of the green and yellow curves for both communication and sensing. And what we see interestingly is that increasing network density always improves sensing, even though the interference would get worse. The improvements in the desired signal strength always outweighs that. Whereas if one looks at the SNR distribution, at least for communications, it isn't the case. There's sort of an optimal density. So this is something that, in the design of networks, one would need to take into account. There's a little bit of tension, it seems, in terms of the densities that one might like for base station deployments between communication and sensing. All right. So I apologize that first.
Could I again ask a question? So
Yes.
it's very interesting. So, I mean, we are used to this sweet spot for communication, right? That too small a cell creates a high interference, too big a cell creates back signal, right? So, what is the rationale or the reason for which you don't have that for the sensing? Because
Yeah. So
interference will be high too, right? So, if you have very small cells, I mean, this guy sensing nearby will also kill you, right? So it doesn't happen here. No, it does. But it's when you have no, it doesn't, right? Because you small cells,
it doesn't seem
high interference, but it doesn't kill you, right? Does it?
Yeah, it doesn't seem to kill you, even though there's a big difference between the SNR capacity and the SINR capacity for sensing. There's still an improvement with decreasing cell radius or increasing density. And I think the reason for that is that in the path loss for the desired signal, let's just say that, for instance, everything was all line of sight. The interference would be something of the form, r to the negative alpha, but the interference path loss. But the desired signal path loss would be r to the negative 2 alpha. So sort of as you sort of infinitesimally sort of change the distance between all the interferers and the desired object to be a little bit closer, the marginal increase in the desired signal is going to be bigger than the marginal increase in interference.
Oh, so this is only for the path loss big one of our polynomial function that you have these results, or if you would have a bounded path loss function, would you have similar results?
So yeah, I guess the path loss we're using is with the polynomial plus the exponential terms. I think the key thing is that you basically have you have a path loss exponent in the desired signal that's higher than the factor of 2. The absorption factor is also being scaled by 2. I think as long as you have this sort of two-way path loss effect where you're basically not quite squaring the path loss, but something that looks sort of like squaring the path loss in the desired signal, you're going to have something that looks like this phenomena. Although I think it would be interesting to look at with different path loss functions.
Okay, thank you. It's very interesting.
Yep. Yes, that's basically the bulk of my talk. I apologize for having to skip some of the analytical sections. But
can I ask also a question regarding the sense? What was the average distance of the targets to the cell? Maybe yeah, here in the picture.
Yeah. So this average. You mean what the meaning of the average cell radius is, or what the? So basically, this average cell radius is sort of the for a specific density, this induces an average cell volume, and then this would be if you divide this appropriately, that gives you the average distance of the cell. So this average cell radius here would be sort of like almost like an approximate, maybe slightly higher. It was more like the worst case, I guess, distance.
Okay, maybe we can. Okay, it was regarding the interference, how you take into account it, but yeah, the interference is always the two is only the reflected, or you're considering also the direct.
Yeah, so the interference would be from other base stations operating in the network.
Okay.
Yeah. So they're generally going to be farther away than the object that we're looking at.
But the signal, since it's reflecting, it takes could take a longer path, right?
Yes. Yeah, it'll sort of be double the distance in effect.
So yeah. Okay. For this reason, I cannot really grasp why by making the base station closer to each other, you don't see the effect of the interference going up.
Yeah, so interference is still going to have a big impact. There's quite a significant drop in these sensing capacities. It's just as you get slightly closer, even though the desired signal is going to be very weak, the improvements in the desired signal for an increase in density is going to outstrip basically the increase in interference.
Okay.
Yeah. Yeah. So yeah, thanks for basically sitting here through my talk. I'll just, I guess, open the door to some more questions. I'd be happy to follow up too with some more in-depth discussion of the analysis, which I apologize I wasn't able to get to. So yeah, I'll just point out too, I think this opens the door to potentially some interesting future directions, looking at, maybe some different topologies, different use cases too, if you're looking at different parameters. I think accounting jointly too for detection and tracking performance in a common framework would be interesting. And we could also potentially use some other types of SG analysis. For instance, the meta distribution could be interesting to look at for sensing. So yeah.
Thank you.
Yeah.
Any question in the room? Also?
Yeah. I mean, there is a sort of sensing sharing in the same way as there is communication bandwidth sharing, right? You may have several objects to be sensed in a cell in the same way as several many objects. And so is there a notion also of sort of capacity per user or capacity per sense, per object, per target, right? Can you, I mean, devise, I mean, things which would be take the load in targets and in users into account as well?
Yeah, I think that would be very interesting. Yeah, I have to think about how to do that precisely. The challenge is then you sort of get into the realm of how one would potentially determine the allocation of these resource elements in a temporal sense, sort of getting in some of the scheduling aspects. But yeah, if there's a way to extend that to talk about the sort of trade-off between the UEs that you could serve versus the objects that you could sense, I think it would be the most interesting way to take this work. But yeah, I've been thinking about that, but have yet to come up with a way that seems tractable.
If you limit the time for the sensing, you limit also the maximum radius, right? Because you need to wait until the signal comes back. And
yeah, as you limit the time that would change the resolution to for the Doppler, basically the velocity of the targets. So yeah, that's another issue, is that there's some hard constraints on what the waveform needs to satisfy from the perspective of the range in Doppler and angular resolution.
Because there is not much in the literature regarding the kind of capacity of sensing capabilities.
Yes, yeah, especially from sort of a resource allocation perspective.
Yeah.
Perhaps another question, I mean, more about the global picture. I mean, assume you can learn about the environment, and how would you practically use that if there are, I mean, it could be obstacles, something like that, to rearrange the communication, to improve the communication. Would it be like cooperative scheme between two base stations? I mean, this UE is blocked, and then you let it be addressed by somebody with the second closest. I mean, what is the mindset in terms of architecture of communication where you would really benefit from sensing?
Yeah, so I think it could, if you're using it to sense blockages, for instance, you could use it to either aid or predict handover or beam misalignment. So if you're, tracking some object and it's in your line of sight beam, or in its line of sight, and it's about to go potentially behind a blockage, given knowledge of its velocity as well, if there is another base station that also knows where that blockage is, that would be able to predict, to determine that the predicted position is in a line of sight, then that could be something that could be useful. I think it would require pretty good knowledge of the relative positions of the base stations. But yeah, it'd be something that could aid in that regard.
Oh, I see. In that case, you would try to learn from the sensing, not only the shape or the size, but also the velocity plus other obstruction capacity, I don't know, of the obstacle, right? That would like to
yes
learn in a higher dimensional parametric space. That was your end, right? Or okay.
Yes.
Yeah. Okay. And in practice, I mean, what are the parameters that people want to learn? What is the dimensions of the vector that you want to learn typically for these 6?
Yes. So there, you know, there's parameters of interest and there's nuisance parameters as well. So, but generally the ones that people care about most are the range, the Doppler, which corresponds to velocity, and the angular position. So, you know, in 2D that would be 3 parameters, or if you have a 3-dimensional space, then you have 2 angular parameters, and it would be a 4-dimensional overall vector for theta.
Thank you.
Other question on which? In the room? So thanks again.